Okay, today's lecture will begin on page indexing and retrieval, and this is the core of all the stuff that Google does, how they go about grabbing the data and storing it in their index and then retrieving it when people launch search queries. So, we'll first talk about indexing, why it's necessary, and some general techniques for making it faster. Then we'll get into the specific details of how Google follows along with that. So, Google's indexing systems architecture, the components that build it, and how it works. As you probably all know, Google is fast. It's not just fast, it's really fast. If you do a typical popular search on Google, it could take about half a second to deliver the first page of results. An unusual search, or one that requires a lot of excess content, might take a second, maybe 2 seconds. So we can go do a quick demo on this. Let's go to Google, and we will search up, I don't know, something fairly common. Let's look up Blackboard site. Boom, and in about 0.59 seconds, okay? The one that I got that took a really long time was looking at movie show times. So if I look, I don't know what's in movies these days, right? I mean, who sees movies anymore? So we'll go check what's on Rotten Tomatoes, find what's in the box office. Aha, new movies. Okay, so Borat, sure, okay. We'll look up that. So Borat, movie film, showtimes. And even that took 0.5 seconds. One time I did it for a movie and it came out to like 1.8 seconds. So I guess it's quick. All right, that's fine. So that's just demos what I'm talking about. If you're doing searches on Google, it gets it really fast, which is especially impressive when you consider how fast data keeps growing. So Google's constantly having to deal with more pages, and all those pages need to be ranked, and there's more content per page, which Google considers in its ranking process. That makes everything trickier. And there are more users spending more time on the internet, generating more content, generating more search traffic. Google's basically a lot busier. Every search entails more work, and there are a lot more searches. So how does Google keep up? Simple answer, indexing. How does indexing work? Well, what is it? Well, first of all, remember that Google works by matching search terms to web page content, starting with text. All right, so if pages had no content other than text, Google would be able to use that text to find matching pages for a given set of search terms. Whatever search terms you enter, Google's going to find the set of pages that contain some of those terms and then rank them. Now, the way Google does it, it keeps this massive index of search terms, basically everything that somebody might possibly search for and all the pages containing them. So, for example, a very small index, suppose you had an internet that consisted of, 11 pages, A through K, and only 3 search terms you wanted to consider. So we had some oddball ZY words like syzygy and zygoma and zizava, which are all actual words, I promise you. So, for example, if syzygy was stored in pages A, B, C, and D, and zygoma was stored in pages B, E, F, and G, and zizava was stored in pages A, C, F, H, I, J, and K, then when a user entered some of those search terms, Google would quickly scan through the index to retrieve the pages containing them. This is a lot faster than having to scan every individual page for every search and verify whether those pages contain those words. So, once Google has figured out the set of pages that are selected, then it applies its ranking algorithm to determine which ones get delivered. So, for example, I'm going to lift this and copy it into Paint. Okay, so first Notepad. That's just some notes I had for office hours today. Where's my Paint? There it is. Whoop. There we go. That's what I wanted to do. Okay. So this is some stuff. Wow, I'm grabbing a lot of things I didn't mean to grab. Okay, so all that other stuff was some video content that I'm doing a little work for McGraw-Hill on the side. Anyway, and this, I am grabbing a lot of outside stuff today. Boom. So suppose I look for my search term, right, my search query. Suppose my search query is syzygy zizva. Okay, that would return pages probably in order A, C, right? A or C, because those are equivalent. They contain both words. Then B, F, D, B, D, F, H, I, J, Okay, right? If I search for all three, no pages contain all three, but several contain two, and all contain at least one. So I might get A or B or C, all of which have two of the words in them, or F, which has two. Okay. Otherwise, I get some of the other ones like D, E, G, H, I, J, K. So the ones with two words, probably the best match. Could apply other techniques like term sequence or co-location to, rank them against each other. Okay, and this is basically what Google does. So it likes to find pages that have all three. That's usually a good match. If it can't find pages that contain all of them, it can find the pages that contain some of them, and it'll give you those. But it's not generally going to return any pages that don't contain any of them. Okay. So the way this works, when a Googlebot scans the page, basically it captures all the words and then inserts the page into the index entry. So suppose there is some new page L is created, and it contains the words Zygoma and Ziziva, but not syzygy. Okay, then L would appear on these two, right? It would go here, get appended to that part of the index, and get appended to this part of the index. Okay, and then everything would be fine. Then the index would be once again complete. That's basically how the process works. Anytime there is a new page created, Google scans it, and I just leave it where it was, and includes it in the appropriate index entries. Or if a page changes and the Googlebots go around the internet and they find that a page has changed, again, they can update the index entries on it. All right. So why is index necessary? Why is indexing necessary? Well, the short version is a relatively small amount of overhead, right? Doing some work, some preparation work, is going to save a whole lot of processing time for every query. So as a human example, suppose you have a big stack of books, right? You have a little library in your house. You have a stack of books, and you wanted to find which, if any, reference Charles Babbage. Now, if you're a human, you might know that Charles Babbage was an early pioneer in computers. However, let's suppose that, like a computer, you have no idea who he is. You have no idea that Charles Babbage even refers to a person, or how he might possibly relate to any book titles. All you know is you want to find within your stack of books which books have some reference to this thing Charles Babbage. So, very slow approach, you might check by reading each book from start to finish. Now, that would be okay if that were the only thing you ever had to do with that library. But imagine if every now and then you have multiple queries for this sort of thing. Well, you don't want to have to go through the full book search for every time somebody launches a query. So, very fast approach, you would look at each book's index, right? You would flip to the back of the book and you would say, oh, there's the index, and I'm going to look for Charles Babbage or Babbage Charles, and hopefully find some entry there corresponding to him. If I don't find it, then I'm going to assume that the book generally is not about this Charles Babbage person. Okay, and it's the same thing with Google, except they have to build the index in the first place, which does entail scanning through every page of every book. Now, let's continue our search example. Suppose this stack of books is very large. It's bigger than just a library in your house. It is absolutely not feasible for a human in real time to look through the books. So let's suppose, again, like most humans, you have only one set of eyes. Then even an index search could be slow, right? If you have a very large stack of books and you have to scan through the index on each one of them, even searching through the indexes could take quite a while. So one solution is to break up the task in what's called distribute it. So distributing it means you break up the task into many slices and allocate each slice to a different person or set of hardware or essentially some processing tool. So with humans, you'd gather n people, right? You'd call up n of your buddies and tell them, hey, I got this job for you to work in my library. You'd split the book into n stacks, and each person gets one substack. Now, the total work in that case is going to remain the same. Still, all the books are going to get scanned all the way through, but because you have a lot of workers doing the job in parallel, the total work gets done a whole lot faster. In fact, it generally gets done n times faster. So a task that might take, say, an hour on one machine or a few hours on one machine, if you apply 10,000 servers in parallel, it might just take a second or so, right? 3 hours is pretty close to 10,000 seconds. So by distributing the job over many machines, you can get the work done a whole lot faster. Okay, and this is essentially the same idea that we do when Google does its indexing in its distributed systems. You have a very large index entry, which might reference millions or billions of pages, gets broken up across multiple machines, and each machine does a small portion of the total work. So, for example, suppose we do a search for something very popular like money. Okay, there's 4 billion and change results on there. If you wanted to store all 4 billion blurbs, right, that would be a lot of space on one machine. And scanning through them to pick out which is the best one based on your personal history, that would take a while on one machine. Even on a very fast machine, wouldn't really be feasible. Google doesn't want to do that. So instead, what Google does, they take this index for money, which again, you can see, contains 4 billion and change results. They break that up into a bunch of slices, maybe 1,000 slices, each of 4 million pages, and they allocate those to a large set of machines, right? Every one of those 1,000 machines gets this 4 million entry segment of the index. Okay. Now, caching. Let's bring in where caching works. So, expand the problem. Your search operation is now popular. You have millions of search requests every day, and a few of those search requests are very common, come up a lot. So, for example, you might have something called a zip distribution. So this is something that occurs in a lot of real-life situations. A zip distribution, which generally has the property that a small fraction of things are responsible for a lot of the total content. So basically, a few of the things are responsible for a lot of the frequency. Okay, so it's going to look something like this. So frequency and then rank. So this would be, you know, rank number 1, rank number 2, and so on. So basically like number 1 and all the way down here to number n, however many things you have. And a zip distribution is generally going to be something like hyperbolic. I mean, I could define it formally, but this isn't a stats class. It's going to look something like this. Okay, so what we see, this is typical of a lot of many real-world phenomena. Okay, a few of the things are responsible for a lot of the results, right? You might have heard this in other ways as the 80-20 rule, for example, but it applies in other ways. So a fairly small number of topics are perhaps roughly equivalent to, you know, everything else. All right, so this is where caching comes in. By caching the results to the most popular queries, we can very quickly respond to them, okay, and make the most users happy for the least cost in terms of memory requirements. Okay, because remember, all the stuff that's cached, you know, this is probably in RAM, this is probably not in RAM, right? Cheap but slow. Okay, so you can apply caching to Google's search, and they certainly do. So in order to do this, imagine one of your people on your team is super fast, right? Blindingly fast, and he can remember all the results from 100 searches. So the first execution of a search happens normally. It still takes him the time to go through and do the search process. But once he's done it, he can recall those search results instantaneously, and any subsequent executions of that search are actually instantaneous. Well, the best way to use that talent, assign that person the most popular searches. And this is exactly what caching results for popular searches is. You have part of your system that is blindingly fast, right, is RAM, and you can store all the results and immediately retrieve them without looking at any hard drives at all. On the other hand, everything else, well, you don't have a team that's all blindingly fast, so these other guys, you use them for the slower searches, right? They're not that common, and you're not making that many people happy if you store them in RAM, so it's better to use that capability on the most popular searches. Also, doing it on the most popular searches reduces the requirements for everything else, right? If this is, say, about half your traffic, then guess what? All of this stuff can happen that much faster because it's not clogged up with looking through all the hard drives for these popular ones. Okay. Questions on any of that? Does all that make sense? I'll take a minute. I'll field some questions if you have any. Does all make sense? We're all good? I hope. All right, moving on then. So, next step is semantics, right? If we accept the possibility that pages are not going to always match the terms exactly, but they're still going to mean the same thing. So, if you're doing this in a basic naive way, like Google used to do it in the 90s, pages can be indexed just by search terms. And this works reasonably well for very rare terms on mostly text pages, right? If the pages are all just text and the words are pretty distinctive, there's not a lot of alternate meanings for them, and they're not used very often, so they don't appear on that many pages, yeah, that's fine. However, for popular searches with ambiguous terms on object-heavy pages, it gets a lot trickier. So remember, Google is trying to use semantics to match the user's intent. So one thing Google will do, it creates entries for term groups or concepts. Okay, so for example, buy a car, right? The terms buy car, Google might empirically observe that that turns out to lead people to car dealerships rather than how-tos for price comparisons, right? So buy car could theoretically mean where I'm going to buy a car or the requirements to buy a car, right? What documentation, what deposits do I need, what credit do I need, or a how-to operation about how I would go about, not getting ripped off when I buy a car. But if Google empirically observes that a lot of these buy car searches are in fact going to dealerships, right, then what Google will find out, something like this. There'll be one set of search terms, buy car, that perhaps lines up where to buy car, or car dealerships near me, right? And Google might observe that all of these things they lead to some pool of pages, right? This pool of pages is maybe something like this. And for buy car, it has one slice. And for where to buy a car, it has another slice. And for car dealerships near me, it has another slice. But we might observe that the slices they get, right, overlap a lot. So for example, maybe buy car gets this slice, and maybe where to buy a car gets something like this. It's a little bit narrower. And maybe car dealerships near me, right, it leads to a lot of the same pages. And based on this analysis, Google's going to figure out, oh, look at that. Whoop, I'm going to say a lot of this is the same, right? So basically, heavy overlap in interesting search results, right, demonstrated by actual user clicks means terms are semantically close or equivalent. And the important thing, Google doesn't need to know what any of these terms means. Google just needs to know they lead to the same place as far as users are concerned, right? So Google doesn't need to understand what the terms actually mean, so it doesn't need to build some sophisticated artificial intelligence. It just needs to verify that users go to the same links from them. Okay, and I hope that makes sense. All right, so Google indexes, incorporates semantics, creates entries for terms or concepts, right? So like this by car example. And these can be integrated into normal search, or they can be displayed separately through the knowledge graph. So for example, right, we saw this before. If I look for something like famous astronomers, right? Google has lists of people, for example, has list of astronomers, and list of famous people, and there's going to be some intersection between the two, right? So if I have a list of astronomers and another one that's a list of famous people, well, guess what? Famous astronomers, that's right here in the middle. Okay, it can use that intersection to deliver this sort of information through the knowledge graph. Okay. Now, search engines certainly consider how terms are used, how often they occur, and the ways in which they appear. For example, as humans, we know if Charles Babbage refers to a human, then we know that Babbage, Charles is also going to be a name, right? With the conventional English language, last name first, comma, then first name. Now, a book index would typically store Babbage, Charles, not separate entries for Charles and Babbage, right? Because again, these books are designed to be used by humans, so it puts the information in a way that humans understand. And the reason, of course, is in most cases there are likely to be many more Charleses than there are Babbages, so it lists the humans by last name first. But as readers, of course, as humans, we see very clearly the difference between the phrase or Charles Babbage and Charles or Babbage. Right here, the name is there, it's intact. Here, even though the words are together, the fact that they're separated by another word changes the meaning entirely. So, how does Google implement this as far as indexes? Well, every index entry for Google is a semantic unit, which can be one or more words that has a specific meaning. Okay, and it can be different sets of words that have an equivalent meaning. Now, determining this sort of thing, the most likely grouping or the intended grouping for a set of terms, that's going to help Google deliver better search results. Okay, so for example, way back when, right, circa 1998, Google worked with exact term matches. And that meant different but equivalent terms would not appear in search results. And this wasn't unique to Google. This is the way it was back then. Okay, so for example, if you were searching for a term that had a number of equivalencies, for example, the Second World War, right, also known as WW2, also known as WWII, also known as, write it out, World War II or World War II, not world, or I don't know, over in the old Soviet Union, they called it the Great Patriotic War. So if you're looking for that, you might find that. And, you know, other countries, languages have their own terms. Okay, so So there's a lot of equivalent terms for it, but if you just searched this, right, you wrote it out, Second World War, then you'd miss all of these unless they were also there in some form as the literal string, the Second World War. So this was a problem. But of course, all these things mean the same thing, more or less, and so they show up in the same index entry now. All right. Another thing, common words, how those are filtered. So normally users won't consider more than a few dozen results, typically far, far fewer, right? Typically, the thing you're looking for is in one of the first few results Google tosses up. So in most cases, a search engine isn't going to deliver everything that matches. It should only deliver a tiny portion of the matches. For example, all right, we did our search for money. Let's see if we still have that here. Yeah, we have it for money. Even though there are 4 billion search results, I can look all the way to the end, and I will very quickly exhaust the list. All right, so probably tap out at about 300. That's usually where these things end, even on big searches. We'll get there. Ooh, that took a little time. How long did that take? That last page took 1.87 seconds. Took a little while. Google didn't think I was going to search that far. But that's the end. Okay, this is the end. That's all there are. That's all Google's going to show me. So page 25 of about 242 results. Even though there's 4 billion search results, Google says, yeah, you know what? Only a couple hundred of these are worth bothering with. So other things, very common words like the word the. The will appear on most English language pages and generally should be excluded because, number one, including the word the doesn't materially differentiate pages, right? Results with or without them are going to be pretty much the same. Also, they add a lot of ranking effort because common words are repeated on every page. So if you included the, basically, number one, you'd have to include an index entry for the word the. Number two, every time your bot scoured the internet, you know, they'd have to update all the pages for that entry for the word the. It would be a massive index entry that would occupy a fair amount of space. And anytime you wanted to include that as a factor in your search, it will slow things down. So for all those reasons, generally you don't want, Google doesn't include the common words like the in the search process or in the indexing. However, having said that, you can see some interesting things. For example, if I look up Chicago Cubs, if I do that in one search, this is what I get. But if I do the same search again, and I do the Chicago Cubs, I do get slightly different search results, right? So here I get official Chicago Cubs website at the top and some stuff here. But if I just do Chicago Cubs, right, I get this knowledge card here of top stories. Here, you know, some of this, here I get an article about Jason Hayward, right? Here I have to, yeah, it doesn't even appear on the first page. So there it is. It appears as a top story down there. So interesting stuff. So there are slight differences. And my best guess about this sort of thing, you can find many searches where the word the doesn't really change anything. But my best guess is perhaps Google has observed somehow a distinct pattern in how people use the word the for sports teams. For example, a younger person might just look up Chicago Cubs, where an older person might look up the Chicago Cubs. And the term the Chicago Cubs might be associated with more with historical things or about broader things about the team itself, about the entire team, whereas just Chicago Cubs might catch a lot of, you know, more detail-oriented articles. That's the best I've got. If you can think of a better explanation, well, perhaps yours is correct. But all I can say is we do occasionally see some slight differences, even though most of the time Google ignores the words the and a and, you know, other very common words. Okay, so a few articles about Google's index system. We'll come back and talk about these over the end. These are basically some things that are good to know. I'm not going to ask you any great details about them, but if you want to take a moment and browse through them, there are some articles basically about how Google does semantic search, how it, Hummingbird, for example, how it implemented semantic search through its entire operation. Once upon a time, semantic search was just a new feature that Google did on a very limited scale, but now it's something that it incorporates into its entire system. Caffeine is a new way processing these index entries. So for example, once upon a time, Google used this MapReduce that I brought up at the end of the first Facebook lecture. Once upon a time, it did that and it worked fine. But as the entries kept on getting bigger and bigger, Google said, you know what, it would be great if we could process these faster and process them as partial entries instead of the entire thing. So Google has broken up the index entries into segments, and it can process changes to those segments separately from each other. So it's no longer using maps, it's using a similar engine called Caffeine to get the work done. It still does that kind of updates, but it just allows it to process faster because each process accesses a smaller part of the system. Then I have a little article about the knowledge graph that we've already talked about. So again, if you want to check those out, you can check those out. They're interesting reading for any of you IT people. Okay, but here we are talking about Google's indexing system itself. So first, let's consider how the problem works. So every request, if I type in a search query to Google, that request goes to a cloud system somewhere, right? We know the tasks. We know basically what has to happen, that Google looks at the term, Google figures out which pages, how to group those terms, which pages match those term groups. Then Google has to pull all those pages from a database, rank them, and deliver some small subset of the pages to you. So we know all those tasks, but we don't know the details of how the hardware is connected or, generally the internals of how it works. And in fact, this is actually pretty typical of how Google works. Everything, as far as they can manage, is an isolated modular task. So draw a picture. If we enter some search query, and that gets dropped in the funnel, to Google's system. I'm going to draw a cloud here. I'm going to draw a nice fluffy cloud in gray, I guess. Okay, and let's fill that up with light gray. Boom. So words go in here, and then cloud, a great mystery. But what it puts out at the other side matching ranked pages. Okay, so we understand the details of how it works, and we don't need to understand a tremendous amount of detail of what's going on inside here. And in fact, within Google, there are a few main points that happens, and we can talk about those briefly, though. So I'm gonna. Number one, query parsing. So Google's going to look at all the terms. Number two, spell checking, right? And other changes. So things like, did you look for the right terms, right? Google's going to say, maybe you misspelled that. So we're going to offer you some other stuff. Then the output of both of these is going to go up here to some kind of box that says right at this point, retrieve and rank the matching pages, and then Google sends them on out. All right, so that's basically what's going on inside Google's process, and that's enough to work on for IDS 200 anyway. So the question, right, number one, what tasks are required? Well, we've discussed that briefly. What's the sequence of the retrieval process? We'll get into that. And what are the associated interfaces? Well, we can see about that, right? The interface is right here. I'll put those in orange. Search terms, that's what it gets. And with the parsing, right, Google sends echoes same terms. Okay, here, different terms, right? For the spell checking says, hey, maybe you meant this, not that. It's going to send out some different terms. Right here, we're going to have same terms. So these together Google gives all the original terms plus a set of possible likely matches, and then this operation sends a bunch of links and blurbs to be sent to back to the user. Okay, so those are the things that happen in the interface. So the input here, accept a set of search terms. The output, the identical search terms echoed forward, and then the same terms sent to spell check, right? Then, I guess I should mention same terms prioritized, right? So it's going to say, here's the best match for what we think. For example, if I enter the words New York City, well, Google knows what I mean. I probably mean that city, right? But if I entered city, York, new, then it's more ambiguous, right? So Google's going to take these terms and come up with likely prioritizations for them. And same thing here, different terms, possibly with different prioritization. Okay. So that's essentially the inputs and the outputs and the tasks. All right, so let's get into it a little more. System architecture. All right, so just like Facebook, and largely for the same reasons, Google doesn't serve everyone in the world from one location. It has a bunch of different data centers worldwide. On occasion, right, Google will have problems. Here's one. Google suffers data loss as data center gets hit by lightning 4 times. That was in Belgium some years ago. Other things could occasionally happen, right? Earthquakes, floods, fires, who knows? All these things could occasionally happen, and it would be very bad if Google's entire operation were in one place. The other thing, just like Facebook, Google wants to keep locally relevant data closer to users. That makes it easier for Google to deliver locally relevant content. And another thing, energy costs. Energy costs are typically a major factor in the selection of locations because all of this number crunching that Google does and all of the sending network traffic out, that all costs money. And Google has a pretty massive electricity bill. Having said all that, it would be possible, it would be architecturally possible, even if it didn't make financial sense, for Google to operate entirely from one location. One of Google's current data centers could probably handle 20, worldwide search usage from 10 or so years ago. Last I checked, I haven't checked in a year or so, but last I checked, Google runs about 15 data centers globally, and it's building more. We could do a quick search on that to see if anything has changed. Let's check. Google Data Centers 2020. Well, 21. Well, there you go. See, that's easy to find. 21 data centers. So it was building more last I checked this. Okay. Now, what is a data center? Well, basically, it's like a giant warehouse full of a whole bunch of server clusters. These are very large buildings. I mean, think about the size of a football stadium or, again, a very large warehouse, again, with thousands or even tens of thousands of servers. Beyond that, the details are mostly concealed from the public. Google's pretty secretive about them. But one of these articles, actually, I could just find it online without even using the link. It has some good pictures of what stuff looks like. Right, so here's one. Good, that's a good overview. So this, right, these great big gray shed type buildings, those are the rooms where the servers are being held. And you can see there's room for some parking, some cars out there. But they're not that big. Let's see if I can get something on Google Data Center. Boom. Here's what one of them looks like on the inside. This is the old picture that's in one of the articles. So again, giant warehouse full of a lot of servers and air conditioning equipment, right? Because all these servers, they get pretty hot. And once they get too hot, they stop working. So if I can find a good overview. Here's a big data center in Singapore. So again, just to give you an idea of the scale, you can see some cars up front. It's a pretty big building there. Okay. So that's what we know. That's what Google's data centers are. And a server cluster, each data center contains, probably tens of thousands of servers. And as we were talking before, these big tasks typically get split into sections. 1 second. There's some domestic nonsense downstairs. Sorry about that. So these tasks, they typically get split into sections and distributed over sets of servers. And parallel operation keeps everything going fast. So again, if you have a large index, let's do this, very large index entry, looks something like this, big rectangle, okay, and then you have a set of, say, 10,000 servers, right? This thing gets processed into 10,000 slices. Each server gets a slice. Okay, so something like this. And then the search results get combined and compared. And then at the end, you get the top 200 or 300 or so results. Okay, so that's why Google needs so many servers around to handle these tasks in parallel and give you the results very quickly. Okay, now functionally it's a lot like a RAID device. So you might ask, well, why did the professor introduce RAID devices back when? Well, a lot of this kind of technology operates on the same principles, right? If you have a RAID device, it allows operating things in parallel. You can read data in parallel. You can write it in parallel. You can sometimes do things a lot faster. So these server clusters, they're functionally similar to a RAID device. The traffic gets handled through a common interface, right? Just like in this image. So boom, the initial index entry goes through some common interface. It gets divided into pieces, just as if I was splicing the data over multiple hard drives in a RAID device. And then there's parallel processing for speed, right? Just like striping in RAID. So, same kind of principles. Oh, by the way, if you're an IT person, this is a pretty good article. It's a little old, but the basic ideas of how parallelism works, it's still a pretty good description about that. So, how the giants of the web store big data. Anyway, so here's a question about Google's hierarchical system. So let's assume for a moment that Google keeps a master copy of all data. Now, we're not sure if one data center is assigned to this role, although we think it's unlikely, right? Google is not particularly forthcoming on how it manages this. We're also not fully aware if Google maintains master copies as such, right? We might just say Google maintains at least 3 copies of any data that it has, and those 3 copies are considered equal. None of them outrank the other, right? It's just as long as all 3 are identical, then any one of them is just as good. If one of them deviates somehow, then the other 2 copies will be used as the master copies to reconstruct the original. And these copies could be stored in separate locations, right? So that seems like the most likely case, but again, Google is not particularly forthcoming on how all this works. But I will say this, Google's data centers are known to have different capacities and content. So the most likely thing, right, it's a reasonable assumption to make that any master copy, if it exists, could be stored in any location. So, for example, master copies of any English language pages could be stored in the United States, whereas anything in Chinese could be stored over closer to China. Anyway, so if a page isn't stored in the local data center, that page has to be retrieved from another data center. And in that case, the local index contains the information about how to forward that query. If a query becomes popular, eventually the local index and the associated page storage will get updated. So how does that work? Well, we'll draw a map. So we'll keep it simple. Suppose we have over here Japan, and here we have LA, not LAX, and here we have New York, and here we have, let's say, London, okay, for the UK. And each of these is a box, is a data center. Now, suppose there's an article on, I don't know, the New York Yankees, baseball team, in case anyone doesn't know. Probably this article will be stored at the New York data center. I'll just use DC for data center. Probably, because it's English language, it's locally interesting. Yeah, probably. So suppose, though, that a lot of people from LA are interested in this article. Perhaps it contains information about a trade with the Dodgers. So even though it's an article listed primarily about the New York Yankees, people from LA area are reading it and searching for it. So what will happen in that case for this particular article, initially, let's do it in steps. Initially, the article will be stored only at the New York data center. Requests will be served by forwarding the request from LA to NYC, then receiving the results back from NYC, right? So basically, if this is an index entry, it is primarily popular in New York, well, then LA is going to look at its index and say, oh, I don't have stuff to do a good match on this set of terms. I got to call New York and forward part of that query for them. So New York is going to send back its blurb of matching results. Over time, though, if the search remains popular in LA, eventually the LA index will be updated, right? So the LA index will contain those same terms that lead to copies of the pages, and they'll be stored locally in LA as well, or at least the blurbs will be. Okay, and that's basically how it works, and it works the same way, for example, locally popular page in Japanese, initially stored in Japan's data center, right? A tourist living in LA planning on a visit to Tokyo might do a relevant search, and that search would be forwarded to Japan, okay? But if the search becomes popular, eventually the LA data center will contain the relevant index segments. Okay, so maybe we're doing some kind of search like best sushi Tokyo, but in Japanese. Okay? Anyway, so those are possibilities. All right. Other stuff. So Google stores a replica of each page that spiders have visited. So somewhere in Google's system, anytime a spider visits a page and Google decides that the page is good enough to be kept in its system because it's not total garbage, Google stores it. So basically, Google has a duplicate of the entire surface web. And obviously, this is pretty big. Now, Google's not going to copy the entire index and entire set of page replicas to all of its many data centers. That would be a waste because most of those pages are not going to be of much interest outside, for example, their local language. So Google applies the principle of localization. Any particular data center is going to store those pages that are predicted to be of greater local interest. For example, things that are about local places or local people or in the local language text or have a history of being requested locally. That's what Google is going to use. So example, there's a lot of assumptions built in for common queries like weather or local events. Inherently, those are going to tend to mean for this location, right? If you're looking in Chicago, living in Chicago, and you just query local events, you're going to get Chicago local events, right? You're not going to get local events from Sydney, Australia, for example. Anyway, when necessary, non-local page content can be retrieved from other data centers or Google's core database if it maintains one. All right. Now, just like Facebook, Google also has to deal with the long tail popularity problem. Even though the majority of searches are for current events, there's a substantial minority of searches for years-old pages. And there's also a surprising amount of perpetual novelty, right? The last data I have on this is from 2013, but in 2013, Google said that 16% of its searches had never been searched before at Google. And a lot of what those are going to be are, for example, new people's names combined with other features. For example, you know, Susie Johnson, Chicago, Illinois, or Fred Jones, Washington, D.C. Things like that, just simple combinations of names and places, or other, just the terms themselves are common, but the combinations of them are not. Anyway, so in order to optimize performance, Google has to continuously update and cache the popular search results. Search results that are popular, Google's going to cache information for those, but the older, less popular pages, just like Facebook, Google absolutely cannot ignore them. It can't just bury that data away and figure that nobody's ever going to look at it, right? So even though we got to the very end of the search on money, and it took a couple seconds to get that last page, yeah, they're not going to be the most accessible because not many people ever proceed all the way on to the last search results. But when you consider that, yeah, 2 seconds isn't that bad for something that Google basically had to dig out of storage and dust off before they sent it to me. Okay. Now, the basic process, like we discussed before, when Google receives the search query and the system is determined it's going to be handled locally, first of all, Google's going to check if the search results are already available from prior searches. Basically, are they cached? Otherwise, the search is going to get processed from scratch. So it's going to parse out the index terms from the query. So it's going to look at the search query string and try to figure out which terms in there correspond to index entries. Then it's going to pull the matching pages from its database. And finally, it's going to apply the ranking algorithms. It's going to say, this page is a better match than this page, and so on. Quiet, dog. And finally, it'll deliver the set of ranked search results to the user. Now, as we know, there may be many pages associated with a particular index term, like money or sports or some of your more popular ones. So, how does all this work? Well, there are 3 different types of servers: index servers, document servers, and spelling servers. And the detailed work of the process: the user enters the query, Google tries to find the index entries that match it or nearly exactly match it. It calls on the spelling servers to check for likely alternate meanings, and then the index servers retrieve documents based on search terms. So all of those documents that match the search term, Google's going to pull those out and look for them. Now, these days, Google doesn't do it from the entire document. It basically keeps a distilled version of the essentials of the document. So essentially, for any matching search term, Google's going to keep a blurb about how that text will appear when in the search result listings. Now, I have an early paper here. This is from back when it was tentatively called Backrub, right? Anatomy of a large-scale hypertextual search engine, right? So this is Google, prototype of a large-scale search engine. This is from 1998, I believe. If I scroll down to the bottom, I can find some details about it. All right, so they had this Backrub project going on. Google was the search engine. And the important thing for this, we're going to look at the results they have. Here we go. Okay, so Al Gore, some of you may recall, he was vice president for a while in the 90s. The initial query, right, how long it took for the first time, and this was a small batch of things. They had like a fairly small batch, you know, number of web page facts, 24 million. So it wasn't nearly as big as it is now, but searching through that database, the initial query for something like Al Gore, because it didn't appear on that many pages, was pretty quick. They could scan through and process and rank all of them because there weren't, you know, there weren't that many. In a cached search, this particular batch of pages, right? So bear in mind, this was not the entire universe. This was just their data set of pages. The cache query could be done in a fraction of that, right? So the total time to deliver the results was a couple seconds. But if it were all cached, it would be 0.06 seconds. So much faster, like 30 sometimes faster. The words vice president, a little bit slower, a lot slower. So close to 2 seconds of CPU time, close to 4 seconds for total time. But if it's a cached entry, it could be done in about half the time. This one, hard disks, the initial search took, all of that took about 5 seconds, but when it was cached, it was dramatically faster. And the term search engines itself, it was a little bit more obscure. It took about 10 seconds to get results on that. Even when it was cached, it took about a second. So depending on how all of these terms were involved and the likelihood that these terms are, broken up across a page, that's what's driving a lot of the difference. So for example, something like Al Gore, those are two words that you're probably going to see together quite a bit, and it facilitates the ranking process. Hard disks, on the other hand, it's, a lot of them will be hard disks together, but you can see them being often apart. Search engines, on the other hand, there are going to be a lot of pages that have engines and a lot of pages that have the word search. But in in the mid 90s, this term search engines had not really gotten that big. You weren't going to find it that often. So it was a lot more work to distinguish one from the other. Anyway, if you're interested, you can dig through this article, but the basic idea of what they're doing as far as how the search engine works and term matching, it's all there. There are those two guys. They're crazy rich now, but that's what they looked like in the 90s. Anyway, little article there if you're interested. If you want to check that out, by all means do so. Okay, let's see. Where's a good breakpoint? I'm hunting around for a good breakpoint because I don't want to. Yeah, we'll do a few more pages. Let's see. Okay, so this is a good point, I guess. We can call it a day here. So tomorrow we'll cover this stuff. We'll go into a little bit more detail about how the indexing process works, and we'll get into some detail about how Google parses the queries themselves, and a little bit of a tiny bit of technical detail about how Google stores the index segments on various machines. And then we'll get into the other stuff. Okay, so I'm going to call the lecture here. This is where we're going to end it. Does anyone have any questions on any of this stuff? I'm happy to answer questions. Right now, we've been keeping it as big overview type things, but we can always get into a little bit more detail. Nothing? Something? Anybody? How are you all doing? All right. Yeah. Yeah. You have kids? All right. Good. Yeah. Well, you'll see what being tired is. Ha ha ha. Yeah. Anyway, I occasionally have TAs that complain to me that they're too busy to do this or that, and they say, "Oh, I didn't know you had kids." Yeah. Anyway, all right. We'll see you all next time, which I guess is Thursday. Enjoy the time off.